I'm convinced that you think aerodynamics is this, something complicated but tangible, or, well, if you're really lost, you might even think that aerodynamics is this, trying out different wings and seeing which one works best. But no, at least not in college, aerodynamics is one of the most abstract subjects. If you weren't aware, there's a good chance I will destroy your life today. Aerodynamics is the big surprise for every aerospace engineer before taking the courses. We think it might be something curious or interesting. Many people likely enter aerospace engineering due to their interest in aerodynamics. But when you start taking the courses, you realize it has absolutely nothing to do with what you imagined. And the goal of this video is to introduce you to what is taught in aerodynamics courses. Let me be the one to take you down the path of madness. And I'd really appreciate it if you left comments on this video. Let me know if you already knew everything I'm gonna tell you in this video and what you think about it, because I'm telling you, it's absolutely crazy. So without further delay, let's get started with the video. Any object, if oriented in the right way and moving fast enough, will be able to generate a lift force greater than its own weight, and therefore it will be able to fly. The hard part isn't flying, the hard part is doing it efficiently, meaning generating little drag. That's the reason why airplanes use airfoils, which can be thicker or thinner, but they'll always have a shape similar to this. Depending on the mission of the airplane we want to design, the airfoil will vary. Very thin designs are used for supersonic airplanes, and very thick designs for flying wings. High-angle airfoils are used for turbine blades, while the most common airfoils are used in general aviation. Well, the goal of aerodynamics, at least in aeronautical engineering, is to study which airfoil will give you good performance. Instead of using trial and error by building a wing and testing it, aerodynamics allows you to study it theoretically. Before we continue, let's do a 1-minute review of important airfoil concepts you'll need for this video. The most forward point of an airfoil is called the leading edge. The most rearward point is called the trailing edge. The line that connects these 2 points is called the chord, and the line that is equally distant from the upper and lower parts of the airfoil. It is known as camber. If an airfoil is symmetrical, its camber will coincide with the chord. On the other hand, if the airfoil has a lot of camber, the chord will not be inside the airfoil. But that's not a problem. I'm mentioning this because the first time I saw it, I thought it was something strange, but there's absolutely nothing wrong with it. Well, thanks to experimentation, it is known that when air passes over the airfoil, the pressure on the lower side will increase, while the pressure on the upper side will decrease. And it's that difference in pressure that will generate lift. Be cautious, reduced pressure doesn't mean the upper part is worse. That's a major conceptual error. What happens is that since there's more pressure below, an upward force is created. Applying a vacuum to a plastic container doesn't mean the vacuum sucks. Rather, it decreases the pressure inside the container. The pressure on the other side is greater and exerts a force inward, and this is where things start to get crazy. The effect that the airfoil has had on the air is exactly the same as the effect that a vortex has. If we replace the airfoil with a vortex, the same thing would happen. The air would behave the same way. The air first approaches the vortex and accelerates on the upper side as it moves in the vortex's direction. The vortex's opposite velocity slows down the lower side. What about Bernoulli's principle? When air accelerates, pressure drops. When it slows down, pressure rises. This seems counterintuitive at first. Putting a vortex in the middle of the air occurs when a ball is spun, such as when tennis players hit the ball with topspin. So, the effect that a wing and a spinning ball have on the air, we could say it's the same. And this is where we introduce potential flow, the basis of aerodynamic theory, which works for irrotational and non-viscous fluids. But first of all, are those two conditions actually met in reality? Well, the truth is they aren't, but it's true that they almost hold for some cases. Air, for example, is a fluid with very little viscosity. It's not a bad assumption to say it has no viscosity in some cases. And saying that it's irrotational means that the air particles individually don't rotate. Be cautious, as they can rotate when deflected by the airfoil, but crucially, each one does not rotate individually. Well, the key to potential flow is that you can separate the uniform motion of the air from a vortex motion. They're treated as two separate things, both of which have an effect on the air in the end, but they're independent. Look, for example, on this website you can visualize the potential flow. And look, when I combine the uniform motion with a vortex pattern, notice the path the air takes. It's exactly the same as the one it takes around an airfoil, because I set up a uniform velocity field and placed a vortex in the middle. Well, to these two types of patterns, the uniform velocity and the vortex, you also have to add the sink and source pattern, the dipole pattern, and the corner pattern. By combining these patterns, you can generate practically any shape you want. For example, an airfoil profile. So yes, in potential flow, what you do is create an airfoil profile by combining the different patterns. Here's my attempt at representing it on the website. As you can see, it's not a perfect profile since I only spent 5 minutes on it, but this would already generate lift. And if you look here at the vortex, a gamma A symbol appeared. This is called circulation. The best way I've found to understand what circulation is to think of it as representing the intensity of the vortex. The greater the circulation, the greater the intensity of the vortex. And since we've said that this ultimately has the same effect on the air as a wing, could we say that wings also have circulation? To simplify things, an approximation is always used. For example, if we have a set of small vortices arranged in such a way that they form an airfoil shape, well, not like the one I just drew. If we move far enough away, we would simply see a line with vortices. And that's why, in the end, airfoils end up being simplified as vortices located along their camber line. And as you can imagine, this really simplifies the calculations. That's why it's done. If we go back to the website for a moment to visualize the potential flow, we can see that the greater the circulation, the greater the curve the air traces around our vortex. If we put a spinning ball, it would have the same effect as the vortex, and the same would also happen with an airfoil. Remember, this airfoil is a combination of various potential flow patterns. We're not actually placing an airfoil there. The airfoil is formed with various patterns. But let's not forget that what we really want is for this mathematical model to represent reality so that it's actually aerodynamics and not just simple mathematics. So depending on how much circulation our airfoil has, the air will flow around it in one way or another. And this is where the CUTA condition comes in, or as it's known in English, the CUTA condition. Because mathematically, all the results are possible. But in real life, there's only one possibility where the air comes out at the end of the airfoil and both the upper and lower parts do so at the same angle. This is called the CUTA condition, or in English, CUTA condition. So, the circulation around our airfoil will be just enough for the air to do exactly that. To leave at the trailing edge of the airfoil and do so at the same angle, both above and below. And after several mathematical demonstrations, it turns out that lift is equal to the airspeed multiplied by the density and by the circulation. So knowing the circulation of your airfoil will automatically give you its lift. But how can you determine the circulation of an airfoil? To understand this, mathematical proofs are necessary. It's also known that if you draw a closed curve, the circulation inside the curve will remain constant. Even if you don't know why, just believe it. And also, even if the curve deforms over time, the circulation inside this curve will remain constant. So, if we place an airfoil at rest and draw a curve around it, the circulation must remain constant. But if we set it's at rest, there won't be any air movement, so the circulation will be zero. But if we suddenly make air start to flow, we know there will be circulation so that the air meets the CUTA condition. So what's happening? How is it possible? Well, because as the air starts to flow around the airfoil, a vortex is created at the trailing edge that moves backward, and the closed curve, which keeps the circulation constant, also picks up this vortex. So the circulation of our airfoil will be equal and opposite in sign to that of the vortex that is forming. In English, it's called the starting vortex, and though I teach in Spanish, we'll also use that term. From the starting vortex's perspective, this is the idea now. The airfoil is initially at rest, but little by little it starts to move and a vortex forms at the trailing edge, until the airfoil reaches a constant speed, generating circulation that is equal and opposite to the starting vortex. A vortex that stays at the starting point. In an ideal world, where there is no viscosity, that vortex would remain at the starting point. But in real life, we know that this vortex forms, but it dissipates because of viscosity. So, in a few seconds, it disappears. When I studied this, it seemed to me that it was completely disconnected from reality. For example, I thought about a plane taking off and traveling from, say, Madrid to Mexico City. And this theory is telling me that the lift generated by the plane throughout its entire journey comes from a vortex that was created at the Madrid airport. Well, yes, the reality is that it does, but the thing is, this assumes constant or sudden speeds. I mean that at the moment when it's at rest, but suddenly starts moving at a certain speed, it does so instantly. And also what it's telling you is that the wing is like a vortex all the time. Theoretically, without friction, one vortex would move forward while another would remain stationary, moving in the opposite direction. What seems strange to us is that theoretically there's a balance of circulations when we know that the starting vortex dissipates. But still, this seemed very theoretical to me, and I didn't even understand how this mathematical theory could work in reality. This is actually when the question came to me, does this work? At first I thought it didn't work and that they were tricking me, I promise you. But over time I've realized that this actually has more usefulness than I thought at first. Honestly, my first thoughts were that this was a fake theoretical aerodynamics, something they made up. I don't even know for what reason. I thought, what is this circulation thing? What does it mean that a wing has circulation? I don't understand the concept. Nowadays, we have computational fluid dynamics that allows us to run simulations using a computer. Super realistic, actually, completely realistic we could say for any aerodynamic analysis we want. What happens is that in the past, and by the past, I mean 100 years ago, they didn't even have computers, so the only way to do any kind of aerodynamic study was with these theories, because the truth is that the mathematical calculations required, the potential flow depends on the desired complexity. But they're not very complex because you can separate, for example, the straight flow from the vortex flow. They're not coupled, which is most important. It's crucial to say it's called potential flow because velocity is seen as a field, similar to a magnetic field with variations generated by a coil. Everything has a relatively smooth shape, the same applies to velocity fields. And that's why the possibility of having boundary layer separation is not considered. In this theory, the boundary layer doesn't exist due to the absence of viscosity. And that's why it only behaves realistically at low angles of attack, where the airfoils really do behave that way. I mean, if we create a sphere using some of the patterns I've shown you before, the velocity field in the area closest to the sphere will do this. This theory is limited because it doesn't account for inevitable separations in reality. It's crucial that you grasp this final point. It's one thing for the mathematical field theory to function, which of course it does, but what we're really looking for is a mathematical theory that can be applied to real life, so that air behaves in the same way. But be careful, because the craziness has only just begun, because everything I've told you so far is about profiles. But in real life, what we want is to calculate the lift of 3D wings, and for that, the following approximation is used. First, the wing is replaced by a vortex filament. We have seen that this can be done, because if you can replace an airfoil with a vortex, what we do here is replace each airfoil section of the wing with a vortex. But in addition, two semi-infinite rows of vortices are added at the wingtip, semi-infinite because they start at the wingtip but then go all the way back to infinity. And the crazy thing about all this is that to calculate the lift of a wing, the same theory used for electromagnetism is applied. The Biot-Savart law. It says that if we have a current carrying wire, that current will induce a magnetic field around it, and here it's exactly the same. We have some wires with vortices around them that will affect the surrounding air, inducing a certain velocity in the air, which of course will depend on the intensities of the vortex. If the vortices have high circulation, the induced velocity will be much greater. In summary, airfoils can be replaced by vortices when we put several airfoils together. We have a wing, and the velocity around the wing is obtained by studying how those vortices affect the air velocity around the wing. It's truly crazy. Personally, it took me many years to understand why this explanation is still used. Aerodynamics is a complex subject that can't be oversimplified or glossed over, despite what some may claim. No, seriously, this is aerodynamics. I say this because those who haven't taken courses yet might think this is covered only superficially. Seriously, is this aerodynamics? There are two things I remember not understanding, and I think I still don't understand the second one. The first is, why did they try to use the same theory that's used for electromagnetism? For aerodynamics, what is this? I believe electromagnetism was a recent discovery at the time, having been found only a few years prior. Well, I don't remember now, a few years ago. So maybe the physicists, engineers, or mathematicians of the time thought that maybe everything could be explained with the same idea of a field. Be cautious, as there's a significant distinction between the electromagnetic field and the velocity field used in aerodynamics. In electromagnetism, the concept of a field is established, and that's how it functions. However, in aerodynamics, what we're doing is assuming that the velocity of air can be treated as if it were a field, to simplify and enable basic calculations. But aerodynamics isn't really like that, it's just that by approximating it, it can start to look that way. And here comes the second question. Like I said, I don't think I know the answer, and that is, why is this still being taught today? This currently makes up most of aerodynamics courses. Well, I honestly think it's for several reasons. The first is to explain to us how aerodynamics began. The second is because many computer programs for calculating airfoil profiles use these kinds of methods. And the third is because it's very simple. And since it's very simple, that's why it's used in computer programs for airfoil profiles. When I say simple, I mean that the potential flow patterns can be treated independently. What I told you about the vortex can be treated differently from the air that goes straight. That's what makes it simple, and it's also used a lot in subjects like, for example, aeroelasticity. I would really like to know your opinion in the comments. What did you think of the aerodynamic introduction? For those who didn't know, and those who already did, I would really like to know. What did you think the first times you saw it in class? I felt deceived. Please share your thoughts in the comments to help this video gain more visibility. And after all the hard work I put into making the animations, I think it deserves it. By the way, for any association, organization, university, or whoever wants to use this video, including the animations in it, you can do so. The only condition is that you please say that it's original mine from this channel. I think the students will really appreciate it, because personally, the first time they explained all this to me, since they don't draw it for you or show it to you, they just tell you, so you don't really understand it. So if you're teachers, you can show this video to your students, because what I'm saying here will really help them understand it. Thanks for watching. Follow me on social media. See you next video. By the way, we've surpassed 100,000 followers today. I don't know when I'll upload this, but we've hit that milestone. That's crazy. I have to go skydiving. Oh my god.